Our last talk for the morning session today is talk of Vassily Manturov, who will tell about photography method. Please start.
Okay, thank you very much. This is a very nice conference. I'm very grateful to the organizers. Today I'm going to speak about a very general method which allows one to construct invariants of lots of objects, actually, 3 manifolds, 4 manifolds, representations of braid groups, and actually which allows one to maybe explain why some solutions, why some concrete why some concrete invariants are really invariant. And actually, maybe if I talk about the very recent development, we understood that digraphite actually fit into that pattern. And this is a very new story which was started in the spring. And actually, I will tell you about the contents of 5 archive papers which appeared here. So actually, we are going to construct invariants of manifolds. Actually, it works for many other things. For example, we can think we have a manifold as an equivalence class of triangulations modular partner moves. And of course, we can write down some equations, but which equations to write and how to solve them? And some naturality conditions will guarantee that solutions are more or less obvious. And sometimes it's better even not to write the equations and just follow pictures. And if we follow pictures, the equations will be written by themselves and can be solved by themselves. And I will explain what it means in a minute. And so I would say it should be a common sense. When I was describing that with Turayev, well, he asked, what do you mean by common sense? I would say maybe из соображений здравого смысла. Okay, so here are some papers and here are some talks. Actually, I gave lots of talks, and maybe a detailed talk is my talk on June the 16th. Well, it's you can see it here, and here are some papers. Well, maybe talking about the story, I will tell you first about my paper with Igor Nikonov, and then I will tell you about my paper with Wang Jian, and then there was a paper with Kaufman, Kim Son-John, and Igor Nikonov. And finally, just in September, we posted a paper with Wang Jian about digraphite invariants. Okay. Well, I have to explain my gratitude to many people I collaborated with. Maybe I have four co-authors for now. Other people haven't yet written a paper, but anyway, we're working. And maybe I can ask Nikolai to show my paper with Nikonov from May, and to share my paper from the archive, MN, yes. And in spring, I was working on some groups called groups Gamma and K, and I understood some very interesting phenomenon that some objects, that some equations which appeared for constructing invariants of 3 manifolds, actually the pentagon equations, turn out to be very useful for getting invariants of braids. I was thinking as a lower dimensional topologist, and I was thinking, I'm surprised. I got an interesting connection, an unexpected connection between 2 branches of lower dimensional topology. And actually, I want to leave it as a black box because I gave talks on that. But anyway, I had this. Yeah, can you scroll it here? In fact, in order to say that we got solutions to the pentagon, that some invariants of braids gave rise to invariants of 3 manifolds and vice versa. The key word, the main crucial thing was that both objects, both topological notions, braids and three manifolds, required a solution to the same equation, actually the Pentagon equation. We listened to Kashaev's talk about the Pentagon equation, and actually sometimes some objects are very ubiquitous. And maybe in spring I was thinking about, well, I'm very happy with my groups gamma. I'm not going to talk about them now because they are something like group counterparts of the Pentagon equations. And then I found a very beautiful picture about cluster algebras, which are related to whatever possible hyperbolic geometry, Coxeter groups, and other things. But maybe one of the crucial things in cluster algebra theory is the Pentagon equation, and the fact that Ptolemy yields Pentagon. You will see those slides in a moment. Nikolai, please switch back to my slides. And yes, and so that was my paper with Igor. And after that, I understood that, well, principally, we can do much more, and principally, we can look at other equations. Maybe someone can say Pentagon, someone can say Matveev, Pergolini, someone can say Biedenhardt, Elliott, someone can say other things, many things which appear in various branches in low-dimensional topology. And if we look at them in more detail, sometimes we can see that they are the same. Okay, and now, well, okay, this is the 2-3 Pachner move. So we can consider three manifolds as equivalence classes of triangulations modulo 2-3 Pachner moves. Well, okay, there are 1-4 Pachner moves. I don't want to go into the detail, but there are Matveev Pergolini moves which will appear here, which are somewhat dual, and we can consider special spines. And more or less, this is the crucial thing one has to do if one wants to get an invariance of three manifolds by using triangulations. And there is a well-known theory of Turaev-Vira invariance coming from triangulations and Pachner moves. But now I want to ask the question, how to write down equations? Well, I'd like to convince you that it would be better not to write them down at all, but rather to draw pictures. Why? Well, because actually, when we want to write an equation, there should be too many different ways of doing that. For example, if we write down a Young-Baxter, some people can write it like that. Some other people can write it like that. And maybe if we just look at braids, we can write it like that. But also there are set theoretic Young-Baxters and many other things. And the same about the Pentagon equation we saw in Kashaev's talk. And the same about whatever else, Biedenhardt, Elliott, tetrahedron, and others. We can think, well, let's think about tensors. Let's think about groups. Let's think about other things. But I'd better draw a picture, okay? And what picture am I going to draw? Well, I want to draw the Pentagon equation. Here is my form of drawing the equation on the bottom. What do I mean? Well, we know that a pentagon has 5 triangulation without additional vertices, right? And those triangulations are related to each other by flips. So we can start with a triangulation and flip again and flip 5 times. And we return to the initial position. And the equation we have was can be written down as follows. We associate some data to the pentagon, and we transform this data by using some data transformation rule. We do it 5 times, and we return to the initial position. And the equation says that if we do it 5 times, then we return to the initial data. And that's the equation. Now, you see, I can restrict myself and say that our data is just some set of matrices. But then I'm too much restricted. I would rather say data. And now there is a very well-known fact called Ptolemy yields pentagon. This means the following. We can look at the Ptolemy transformation. We know that for an inscribed quadrilateral with a side length ABCD and diagonals X and Y, we have XY equals AC plus BD. And the Ptolemy transformation means that we take this quadrilateral with one triangulation with one diagonal and replace it with another diagonal. We replace it with another diagonal, and then when we replace it, we change the label. We had X and we get to Y, which is AC plus BD over X. And there is a very well-known fact that if we put some labels on edges here and of the triangulation and two diagonals, and do this transformation 5 times, we return to the same polynomials. Of course, this can be proved by brute force. But I want to say actually that this can be proved without writing anything, without making any calculations. And in some sense, the photography method means that we can solve equations without even writing them by some naturality conditions. So we can have some data, and we have some data transformation rule. And here is a concrete example. By a data, we mean a triangulation. By a data transformation, we mean that we pass from one triangulation to another by a flip. You can imagine we have higher dimensional moves and so on. And now I want Nikolai to show my paper, Manturov 1, number 1, Manturov 1GN. And this is the paper where I think this method was formulated, and maybe we can switch to page 2, I think, or maybe page 3. Yes. No. Maybe earlier. There is a formulation. There is a formulation. Yes, we take some photos of the picture. So by a picture, we can think that we have a manifold, and by a photo, we can think that there is a triangulation, and we associate some data. For example, we associate some labels to triangles or to maybe edges or something like that, and then we get from one state to another. We get some data transformation law. And we get some equations like pentagon. Actually, what I have in mind, I have Young-Baxter, hexagon, Pachner, higher dimensional Pachner, and many other things. Some of them are already written, some of them are not. And then if we have such a data transformation rule, and if there is some naturality condition, then we may get a solution for free. Well, actually, there was another story some years ago. Igor Germanovich Koripanov came to me and said, and took some solution to the pentagon equation from the pocket. What did he mean by his pentagon solution? Nikolai, maybe I can ask you to scroll some pages, forward. Yes. So there is a product of 5 matrices. Yes, this is okay. Okay, so he took such a picture and said, okay, let's take a triangulation of a pentagon, and let's associate some number to each triangle. And then if we perform a flip, we get from from 2 triangles to 2 other triangles, because we flip inside a quadrilateral. And then we can make a linear transformation. Which is expressed by a matrix. And he said, okay, let's take a certain field with elements zeta1, zeta2, zeta3, zeta4, zeta5. And here is a 2x2 matrix, which corresponds to a flip from 2 triangles to 2 triangles. And here is a product of 5 matrices, 3x3, where 1 triangle stays unchanged and 2 triangles are flipped. And then the product of 5 matrices is equal to the identity matrix. He took it from the pocket. And I was puzzled a little bit because, well, I had a pentagon and its solution in the form of labeled edges, and now I label not edges, but triangles. And equations look differently. but maybe there is something in common. And yes, there is something in common. Actually, there are some local transformation rules. So roughly speaking, we can say the following. If we have a pentagon and its diagonals, then having 5 edge lengths and 2 diagonal lengths, everything is prescribed once forever. So roughly speaking, if we have such edge length and a diagonal length, then from 2 diagonals we can recover any diagonal length. And that's why whatever way we go, if we return to the initial position, we will get to the same, and that's why we get a solution. And we can play a similar game with areas. And we played that game with Jayan, and we got to Korepanoff's solution. And then I understood that we can go much beyond areas, or we can go much beyond areas or length or something else. For example, maybe it's not written in my slides, but I just say it verbally. Assume we have a quadrilateral with edge length A, B, C, D, and a diagonal X. There should be a formula for the other diagonal, which is Y, in terms of hyperbolic geometry. In Lobachevskian geometry, there is a formula Y, which is some function f of ABCDX. Well, I claim that if I perform this 5 times for such a triangulations, I will return to the initial position. Why? Well, because I can glue 5 triangles together, and if I glue 5 triangles together, I will get a pentagon, and in this pentagon, everything is fixed once forever. Everything is fixed, and we know once forever the length of other diagonals. Of course, there can be some criticism, because people can say, okay, edge length are something coming from geometry, and they cannot be arbitrary. There is, for example, the triangle inequality. But an inequality is a piece of cake, because if we have an inequality, then we can say, okay, here we have some equation, say polynomial equation, and it holds, provided some inequality holds. But if polynomial equations hold for some open set, then they hold everywhere. And then we can forget about geometry completely. We know where those solutions come from. Okay, we can look at them and prove them by brute force. When we prove them by brute force, we can forget about length and put whatever elements of fields and so on. And that's how we prove the Korepanoff solution. Okay, maybe I'd like to go back to my slides, and maybe up to August, the thing I was mostly thinking about was my work with Lou Kaufman. Nevertheless, I want to say some words about 3 manifolds, and actually 3 manifolds are calculated more. And okay, so for 3 manifolds, we can say that we have this Matveev-Pergolini move. You can say that this is something dual to the Pachner move. Of course, for Matveev-Pergolini, we should say that we deal with special spines. This is not quite dual to the triangulation. We should take a manifold without a ball. We can say that there is only one vertex, but these are minor things. So the main thing is that we are looking for a solution to the Pachner move, or to the Matveev-Pergolini move. And we get some equations. So this is an equation for Q minus 6J symbol for derived zero invariance. Well, I just dropped one weight, but this is an equation. And I want to say this is exactly the Matveev-Pergolini, the Pachner, the tetrahedron, and so on. And now I want to give you a solution to that equation, and this solution goes for free. What solution? And the solution is as follows. Let me say it in words. Assume we have a quadrilateral with side length ABCD and 2 diagonals X and Y. And assume we have another quadrilateral ABC prime D prime with diagonal X and diagonal Y prime. Then there exists a unique Z such that we get 4 quadrilaterals. I would say for that I have A, Y prime, Z, D, and so on. So, well, but saying it in English, what I have said just now means that if we have 2 quadrilaterals with 3 common vertices, and they're both inscribed, then the three remaining quadrilaterals are inscribed. And this is obvious because if they have 3 common vertices, then they are inscribed in the same circle. And on that circle, I get, all those 5 points and everything is inscribed. And actually, this is a picture for a solution to that equation. Well, of course, there is a tiny moment which one can handle and which we handled in our paper with Igor. And this moment is that, frankly speaking, 2 points can coincide, or even all 3 points can coincide, and then there may be not only one circle, but many circles passing through coinciding points. And this is a technical detail, but nevertheless, we can write down equations which would give me invariance of 3 manifolds. I would say to derive zero-like invariance, what sort of equations are there? Well, we write down the inscribedness equations. So we write down the inscribedness equations, and so we write it down for any true vertex. At a true vertex, we have 6 wings, and for 6 wings, I can say that this is a quadrilateral with 2 edges. And actually, this solution is a solution free because if 2 quadrilaterals are inscribed, then the remaining 3 are inscribed. And that led us to our paper with Nikonov, and actually in the paper with Nikonov, we formulated a theorem. So here are butterflies, here are exact definitions. So actually, we constructed a system of equations. And the solution to that system of equations was an algebraic manifold, and actually some stability class of that manifolds. A manifold is an invariant of links. Well, why do I take Z2 here? Well, Z2 is because I don't want to pay much attention to the signs. Actually, AC plus BD equals XY. Where should I have plus or where should I have minus? I want to forget about that. Then the formulation of the theorem was that, so this is my theorem with Igor, that we have some equivalence class of fraction field, and actually equivalence class is the tribute we pay to some coinciding points and some situation when there is more than one circle passing through coinciding points. But nevertheless, the key idea, which can be proved by brute force, is that we have some naturality condition. We have something like, if 3 points are on the same circle, then and if we have 4 inscribed, and if we have one quadruple which is inscribed and the other quadruple which is inscribed, then all 5 points are inscribed. And this is the crux of the matter. This is why we get a solution to that equation. We even don't know what the system of equations is. You see, what is the system of equations? We can say, okay, we have a triangulation, and then we can, with this triangulation, we can associate edge length. And we can have a formula how to transform edge length, say by using Ptolemy or by using something else. But maybe we can say, okay, we have not edges, but areas. And then we can go to some textbook on geometry and see some formula for areas. We can see some formula for areas in the hyperbolic space. We can see some angles. Many of that is not done yet, but one can easily predict how it should go. And of course, there should be some subtleties like division by zero, like some other things, and this should work in general situation. And actually, this general situation has been studied in our paper with Lou Kaufman and Igor Nikonov and Kim San-John, which was posted, I think, in July, where we were talking about higher Pachner moves and invariance of 4 manifolds and actually invariance of n manifolds. And here is a lemma which is obvious, but nevertheless it's crucial. So we can look at points in Euclidean space so that we have n plus 2 points in total, and if we take n plus 1 points, that they are not generic, they belong to the same plane, and if this happens for 2 n plus 1 tuples, then it happens for all n plus 1 tuples. This is like, you know, if we have 4 points, A1, 2, 3, A, B, C, D on the same plane, and A, B, C, F are on the same plane, then all A, B, C, D, F are on the same plane. Hence, whatever quadruple from that phi we take, we would get them on the same plane. And this means that we can write down some system of equations. So if some system of equations is satisfied for one quadruple and for another quadruple, then it is satisfied for the remaining quadruples. And the same happens in any dimension. And this is the clue to constructing invariants in higher dimensions. And actually, in the first version of our paper with Nikonov, Kaufman, and Kim, we just handled the 2-4 Pachner moves and 3-3 Pachner moves. But for 4 manifolds, we also have 1-5 Pachner moves, and we spent some time, and finally, we got an invariant of. So actually, so I just comment on slides. Stable equivalence class is something like we need to do to get invariance. Well, frankly speaking, we can say the following. So if we have say a bipyramid in 3 space, A, B, C, D, and then A prime. This is one bipyramid. And we can take another bipyramid, A, B, C, D, A double prime. And if we know the data for that, and for the data, we can say edge length or areas or whatever. If we know that we have enough data here and enough data there, then of course, we can take not only 5 points, but all 6 points. And for any quintuple of that 6 points, of that hextuple, we can restore the whole data. And this is why, and this is more or less the explanation why we can have 2-4 Pachner move invariants and 3-3 Pachner move invariants. This is the clue. But as for 1-5 Pachner move invariants, and actually maybe 1 n plus 1 Pachner move invariants in the case of n-dimensional manifolds, the situation is a bit different. So roughly speaking, if we so what is say a 1-4 Pachner move for 3 manifolds? It means that we have a tetrahedron, and we add a point in the middle of that tetrahedron. And of course, we will get more degrees of freedom. So this point can move. And so if we write down equations for the initial tetrahedra for the data, whatever this data is, length, areas, angles, then this new point will have more degrees of freedom. And this means somehow that the solution to the initial system of equation will get stabilized. We will get more degrees of freedom, but this degrees of freedom well, is somewhat tame. So we can see that more or less the system of equations will get stabilized, and the algebraic manifolds will not change drastically. Okay, so that's why we get to invariance of 3 manifolds. So roughly speaking, we could take our considerations in the paper with Igor and just copy it for decays. And okay, for example, we can take that 5 points are on the same sphere. Okay, this is an equation. And we can take another, some other 5 points on the same sphere. This is another equation. And if 2 equations hold, then the remaining 4 equations hold. And this is actually the verbal description of the 2-4 Pachner move invariance, which is handled in this situation. So this, and actually 3-3 Pachner move goes the same way. The only thing is that for 1-5, one should take more care. And actually, here is some 3-3 Pachner move. So we have, say, data for, well, pentahora. Well, I don't want to go into the detail because I have lots of slides. And so in the 3D case, we had that Pachner moves. But frankly speaking, I was cheating you a little bit. I was cheating you a little bit when I was talking about even 3 manifolds, because when I was saying that Ptolemy yields pentagon, I was saying that we get a solution to the pentagon for free. So roughly speaking, I was saying the following: assume we have a pentagon with edge length A, B, C, D, E, and with 2 diagonals X, Y, and let A, B, C, D, E, X, Y be some formal variables. Then we take these formal variables and perform 5 Ptolemy transformations, 5 flips. We will return to the initial position. Why? Because if those 5 points lie on the same circle, then they do lie on the same circle and we have Ptolemy everywhere. But you see, the condition that they lie on the same circle is not something we get for free. So actually what we can say without checking Ptolemy yields pentagon by brute force is that if A, B, C, D, X, Y satisfy some condition, then everything will go well. But there is another geometrical interpretation we took with 1GN. May I ask you to show the, Nikolai, may I ask you to show Manturov 1, number 3, number 2, no, Manturov 1, excuse me, Manturov 1, number 1. Yes, this one, yes. And maybe I want to scroll to the paper when we have something called, before, but we have hyperbolic length, maybe hyperbolic length, a nice picture borrowed from a paper by Anna Felix, before as hyperbolic, yes, this one, okay. You know, these are not length, and these are not, this is not the Ptolemy for inscribed quadrilaterals, but this is something called hyperbolic length. I don't want to get details, but I want to say the following: if we have some ideal quadrilateral with its 4 sides and diagonals, and we get some horocycles and cut sides, then there is a well-known equation which looks pretty much the same as the Ptolemy equation for those lambda length. So, but in this situation, if we have a quadrilateral, these lambda length may be more or less arbitrary. More or less arbitrary means that we may impose something like in a triangle inequality or something like that, but we need not imply too much equalities. And more or less in this case, we can say, okay, for a quadrilateral with a diagonal, so for those 5 lengths, they can be almost arbitrary. And if we take a pentagon with 2 diagonals, 7 lengths, they can be almost arbitrary. So then we have an equation which holds almost everywhere for free. So the fact that Ptolemy yields pentagon holds for free because of the hyperbolic lambda length. And that's a very impressive fact. So we have some equations which are solved for free And then we, of course, we can prove them by brute force. And that's why we can predict lots of other things. May I ask you to switch to my slides again? Well, I want to be quick in the remaining part of my talk. So for 4 manifolds, we had something like state sum formula. So what is the state sum formula for, say, Turaev-Vero invariance for 3 manifolds? We took a certain palette of colors and we're coloring 2 faces of a spine, of a special spine. And then we take a certain sum over all 2 colorings, and then we took a product over simplicity. Then we took some products of weights of butterflies. So roughly speaking, we were taking all butterflies with 6 wings, and there was a weight of each butterfly, and then we were taking those weights. So in my situation here, you need not think of D from 0 to dimension M. We can say that we color only top dimensional cells, and we color those top dimensional cells, and then we say, okay, may this be 1 if may this weight of a butterfly be 1 if we have an inscribedness condition, and may it be 0 otherwise. So if we have 4 points and the quadrilateral is inscribed, then we are happy. Otherwise, we're unhappy. And you see, we can look at the Biedenhardt-Elliott equation, which looks like this. And so for the Biedenhardt-Elliott equation, people can say, oh, what a long equation. But you see, if I draw a picture, I can say this. You see, I can say, okay, A, B, C, D, X, Y gives an inscribed quadrilateral. And A, B, C, D, X prime, Y, A, B, C, X, C. Well, if we have 2 inscribed ones, and then if they are inscribed, then we can find a unique D so that the remaining are inscribed. And you see here, this is just the case. So 2 things are inscribed. We have 1 times 1, and here 3 others are inscribed for exactly 1 D. And this is how to explain that we get solution to Turaev-Vero. Well, you know, this is not exactly a case when we have Turaev-Vero invariance, because our palette is not finite. And frankly speaking, we cannot take a sum, but we can write down a system of equations which is very much like Turaev-Vero system. But we can take length integer or maybe from whatever fields. So first, geometry predicts which equation to write. Then we prove them by brute force. And then we can take it over some algebraic fields, whatever else. Actually, for 3 manifolds, something is calculated by Igor. For 4 manifolds, we have a theorem. For n-dimensional manifolds, we have a theorem for all moves except maybe 1 n plus 1. So for 4 manifolds, we handled the 1,5 Pachner move. For manifolds of further dimensions, we have handled all moves except the last one. So, okay, so this is a general formula of the state summation. So now one can look at the following challenge. So you see here in my previous picture, I said, okay, our weights are only 0 or 1. Our weights are just 1 if something is inscribed, or I don't know, something is good, and 0 if something is not good. So if 4 points are on the same circle and some other 4 points are on the same circle, then all 5 are on the same circle. But maybe we can put some weights, and actually here I can put some weights, and more or less I would say that here are the main keywords. Weight is an weight is an area and is a cocycle. Of course, this can look like a black box, but more or less in our paper with 1Jan, the only thing we used to show that Korepanoff's solution to the pentagon equation was really a solution, the only thing we needed was that if we have an area of a quadrilateral, then it equals the sum of areas of two triangles. So roughly speaking, if we draw maybe I draw a quadrilateral here, and I can say that we have this sum A plus B, which is equal to that sum C plus D. And you see A plus B, if we forget about signs, we can say A plus B plus C plus D equals 0. And this is a sort of co-cycle condition. This is a sort of condition that we associate some numbers or maybe some elements of some group to faces of the tetrahedron, and the sum of faces of a boundary is 0. So a co-cycle is something which is 0 on boundaries. So roughly speaking, we can get co-cycle condition to get some more features, some ways to upgrade this. And this was actually some crucial observation in my last so you see, this is the formulation for my paper with Kaufman, Kim, and Nikonov. And actually now I want to say some, so first I say some words about further directions for Kaufman, Kim, and Nikonov. You see, you may have any sort of equation like 5 points are coplanar, or 5 points are on the same sphere, or something like that. And you can have Kelly-Menger formulas, you can have any other formulas from various geometry textbooks. And presumably they should give something nice. They presumably should give something nice. And in the paper with Kaufman, Kim, and Nikonov, we listed lots of various possibilities for equations we can check. For example, for 4 points, we can take such determinants, and then we can say, okay, if 2 determinants are 0, then the remaining 3 determinants are 0. Just because of some common sense considerations. Because if something is coplanar and here something is coplanar, then they are all on the same plane. And we can play similar games with non-Euclidean, with hyperbolic geometry. And I'm suggesting everyone to join such projects, because you can take a formula, your favorite formula from your pocket, and then you will presumably get a solution to the pentagon in its concrete form. So you will have a pentagon, well, maybe not for polynomials, maybe for some trigonometry, but you will get a solution to a pentagon, and then you will get invariance of braids, invariance of manifolds, and so on and so forth. So we listed some situations with hyperbolic signs and so on, and we listed some formulas, and if 2 of them are good, then the remaining ones are good. Okay, one more thing which should be good for students. This is a formula by Sedrahyan Mozaini. Maybe it was known to ancient Greeks, I don't know. So the formula for the other diagonal of the quadrilateral in terms of edge length and the diagonals, it's not as nice as the Ptolemy formula, because nothing is assumed to be inscribed, but presumably it gives a solution to the pentagon. And presumably we have something similar in higher dimensions. Okay, well, and maybe some last words about the Day-Graphitan invariance. This is my very last paper with Wang Jian. And actually here, before passing to that paper, I would say, what were we looking at in my previous slides? I would say, if we deal with tetrahedra, then we deal only with edge labels, because dually we were looking at spines And for spines, we were looking at cells of higher dimensions. For example, spines of 3 manifolds, we were coloring 2 faces. 2 faces correspond to edges. So we played with edge length. And we can say, why? Well, maybe we can take some other data. Maybe we can take areas. Yes, we can take areas. And this was done in my previous work with Wang Jian. It was Korepanoff's solution. But maybe we can take both edges and length. And yes, and the answer is that if we go this way, then we will get de-Graff-Witten invariance. And in some sense, de-Graff-Witten-like invariance, I don't want to say what it means de-Graff-Witten-like, are a partial case of the photography method. And just recently, when we already posted our paper on the archive, Wang Jian drew my attention to a very nice paper by Kevin Walker. In his paper, Kevin Walker gave a very general state sum formula for invariance of higher manifolds. However, and this formula was good for describing Turaev-Viro, de-Graff-Witten, Crane-Yetter, and other invariants, but he worked not with triangulations, but with handles, and maybe this is challenging to translate our work into the language of handles. Actually, here are some formal definitions of what de-Graff-Witten is. So we have some group, we have some complex, but maybe the crucial thing we have for de-Graff-Witten is as follows. We have some laws for data transmission law for edges. If we associate some elements of the abelian group to edges, then we can say, okay, this is additive in terms of if we have an edge AB and an edge BC, then the label of the edge AC should be equal to the sum. If we are in the abelian group, we can say sum, not product. And this is one part of the naturality. One part of the naturality is that we have naturality for edges. But there is also one more condition, and actually to understand de-Graff-Witten, one should look at cocycle conditions. But here I would say a cocycle is a volume, and that is crucial, and more or less this obvious lemma is a crucial lemma. So if we put a simplex into a hyperplane of smaller dimension, like if we draw a tetrahedron on the plane, then the sum of areas will be 0. Well, the sum of areas with signs. So for 4 triangles, the sum of 2 is equal to the sum of other 2. And this is actually the cocycle condition. And this is how to explain why de-Graff-Witten fit into the photography method. Okay. Well, I think my time is going to be over, and I want to mention some further directions. So for example, number 1 can be good for students who really like calculating. So take the Sedra-Mozzani formula and check the Ptolemy. Of course, the brute force will give you the answer, but when you get to it, you will see some details, you will have some division by 0 and other things, which can give further directions for invariance of braids, manifolds, and other things. Okay, of course, there are Sedra-Mozzani-like formulas in 8 dimensions. Well, why length? Maybe areas, and this was done with Wang Jian for Korepanoff's solutions, and maybe it will work. Maybe it will work for dihedral angles. For example, we can glue our manifold of ideal tetrahedra and work with dihedral angles. This was a problem I posted for Roman Dribas, and actually we're now thinking about that with Kim Son-John and Lilia Grunewald about dihedral angles. So we can get some formulas for ideal tetrahedra, and again, we will get solutions. And here we put something on edges of 3-dimensional tetrahedra, and this will give solutions to 2-3 Pachner moves and so on. Why geometry? Maybe sets theory. You see, when I was saying areas, I did not assume any hyperbolicity, any homogeneity, and so on. When I was saying areas, I could say I associate some number to a face. But you see, this number need not be any geometrical. But maybe we can play with some set theory. Maybe we can associate some set theoretic things. Well, actually, one can play with cross ratios. For example, if 4 points are on the same circle, this means that we have in complex numbers some cross ratio to be real. And if for 2 quadruples it's real, then for the remaining 3 quadruples it should be real, and that presumably should give rise to invariance of free manifolds. It's not yet done, but well, of course, we understood de Graaff-Witten. It's better to understand Krang-Getter. Of course, it's challenging to understand the work by Kevin Walker, and this is what we are doing now. So here are our papers on the archive. Here is the paper by Kevin Walker. I want to cite Matveyev. I want to cite Pachner, Sedrahian Mazeni, and a beautiful paper by Anna Felixson, where she was talking about Ptolemy and about how Ptolemy yields pentagon. Well, and I think my time is over. Thank you.
Thank you very much. Let us thank the speaker. Are there any questions or comments?
Yes, I have a question. Can we go to the slide, to slide 21?
Just a moment. Just a moment. Yes.
Do I understand right the meaning of this statement that when you are given a spine, you assign a variable to every two-dimensional cell of a spine?
Right.
Yes? And for every vertex, you write the equation written on the previous slide, like AC plus BD plus Y equals 0. So the coefficients are Z2, so signs do not matter.
Yes.
And you quotient by this equation. Quotient what? What do you want to quotient by this equation?
Well, I associate variables to 2 cells, and I take the free module generated by. So actually here we have this commutative algebra P of S, and then we take the fraction field, and then F of S, and then it's quotient. So this is
the variables are you want to regard all the variables as invertibles, right?
Well, that's why I passed to the fraction field. Yes, because yes.
Okay, then I have a very bad news. For any 3 manifold, you can take such a spine that these relations will generate the entire field. So you will quotient and you obtain 0.
No.
So the second bad news. So the bad news that it is not actually invariant. The second bad news is when you choose the spine carefully, then the quotient field that you obtain can be described in quite standard terms, in quite well-known terms, in terms of the variety of SL2 representations of the fundamental group. So the problem is that even when it is invariant, it is kind of a well-known invariant. And the problem with the use of this invariant is how to compare. So you have two invariants for 2 manifolds, but how would you? This is more or less the same as to analyzing SL2 representations of the fundamental groups, which is, well, why do we need to consider this construction when we can directly define this variety?
Well, you know, when I look at paper by Kevin Walker, for example, he says, well, here are de Graaff-Witten invariants. I give a new construction which defines, for example, de Graaff-Witten invariants. Of course, someone who just wants, looks at, has a goal to distinguish between two manifolds from the list and construct the census can say, okay, this does not give me anything new, but some other people can say, okay, we have constructed a very large, a very new way, of course, a very new way which generalizes this one, that one, and that one, which generalizes too many things. As for this, the fact that it's non-trivial, well, it's something is calculated by Igor Nikonov. You can look for our archive publications. So as for other things, I just said, okay, take this hyperbolic geometry, take here length, take here angles, take here something else. Here you can take many things. Of course, immediately, we could not calculate immediately everything. For example, the calculation of de Graffit invariance of the whole story, especially in higher dimensional case. Not too much was calculated. You are free to join us. And
but I want to repeat, if you take a spine not carefully enough, this what you call invariant actually collapses. You will quotient a field by itself. You will get zero.
No. If I take
I can tell you
there is one minor thing. There is one minor thing about spines. There is one minor thing. We should not have spines with less than 3 vertices in order to be able to apply Matveyev-Pergolini moves. But I think this is the only case. This is the only case when which we should take care of. Okay.
Spines with
with less than 3 vertices, I think. But otherwise, we cannot apply Matveyev-Pergolini, and it should be something.
I think you should at least avoid. If you look at the dual triangulation, you should avoid loops in the triangulation.
Yeah, so, but this is a minor thing, you know. If we have loops, you see, we can avoid it easily. It's really of course there is a difference between triangulation and decomposition where all cells are simplices, and I think many speakers during this conferences abused the word triangulation by allowing 2 simplices to intersect not properly, and so did I. Of course, many people abuse the notion of graph by allowing loops or multiple edges. But of course, this is a minor thing, and you perfectly know it. Okay.
Yeah, but when you speak about spines, how many components?
Me, we postpone this discussion to
okay.
Communication. Maybe there are other questions. Oh, if not, let us thank the speakers. And that is all for our today's session. Thank you.